Decentralized finance eliminates centralized intermediaries by replacing human management entirely with immutable, unalterable code. These smart contracts execute on the Ethereum virtual machine. The Ethereum virtual machine, or EVM, is the decentralized runtime environment that processes every transaction on the network. Once a contract is deployed to the EVM, the architecture forbids hot patches or simple rollbacks. A single localized logic flaw becomes a permanent fixture of the network. If an attacker exploits it, they can instantly drain billions of dollars in liquidity. Because code cannot be fixed post-deployment, auditing functions as the primary multi-layered risk management protocol, preventing financial contagion. In a trustless environment without central circuit breakers, ecosystem security relies entirely on comprehensive pre-deployment verification. DeFi protocols interconnect to form a highly composable architecture, often referred to as money Legos. This architecture forces distinct protocols to rely heavily on cross-contract trust assumptions and transient accounting to execute complex transactions. External data oracles feed real-world information into this web. Oracles are third-party services that supply blockchain networks with off-chain data, like live asset prices. Integrating them introduces new attack vectors if the data feed is manipulated. A localized vulnerability in one specific contract cascades through the network via automated cross-contract calls, compromising connected protocols. Traditional finance contains breaches through centralized authorities that freeze accounts and isolate systemic failures. Decentralized protocols do not exist in isolation and lack these kill switches. An unaudited contract threatens the systemic stability of the entire ecosystem. Securing these interconnected systems requires a tripartite approach: manual analysis, static analysis, and dynamic testing. Modern smart contracts execute intricate state transitions and utilize decentralized governance upgrades to modify network parameters on the fly. Automated tools process mathematics flawlessly, but they lack the capacity to understand a protocol's business logic or intended economic assumptions. Human security engineers conduct manual code reviews to find the unknown unknowns that software cannot contextualize. Engineers map the theoretical economic incentives outlined in a protocol's white paper directly against the raw Solidity logic. Solidity is the primary programming language used to write smart contracts on the Ethereum blockchain. Manual review identifies code blocks that execute perfectly from a technical standpoint, yet inadvertently create a profitable economic exploit for an attacker. Manual review is the mandatory first line of defense. It is the only layer capable of identifying economically flawed protocol designs before they are exploited. The second layer of the audit stack is automated static analysis. Static analysis evaluates smart contract code strictly by reading its structure, without executing the logic in the EVM. The process compiles Solidity source code into an abstract syntax tree. An abstract syntax tree, or AST, is a hierarchical, node-based representation that maps the syntactic structure of the source code. The AST allows auditors to visually and mathematically map inheritance, data flow, and control flow across the entire contract architecture. Static scanners like Slither or Mythex sweep this AST to identify known syntactic vulnerability patterns. These scanners excel at catching standard reentrancy bugs, integer overflows, and timestamp dependencies. The primary advantage of static analysis is its infinite, rapid scalability across massive, multi-contract codebases. Its primary limitation is a complete lack of runtime context. Because static analysis cannot simulate EVM execution states, it achieves extremely low statement coverage on complex branch jumps, generating massive amounts of false positives. Static analysis guarantees foundational syntactic hygiene, but its theoretical nature leaves complex, real-world execution paths completely unverified. To catch what static analysis inherently misses, auditors deploy the third layer, dynamic testing. Dynamic testing executes the compiled smart contract code within a controlled, simulated EVM environment. This environment enables fuzzing, utilizing specialized testing tools like Echidna. Fuzzing programmatically bombards the contract's functions with massive volumes of randomized and extreme boundary value inputs. The contract's state machine handles these inputs seamlessly under normal, expected conditions. A bizarre, unexpected edge case input can force the contract to break and enter an undefined state. This method exposes critical vulnerabilities, like runtime memory management failures and deep call stack overflows. These bugs are invisible to static analysis because they only manifest under highly specific, unexpected execution conditions. Dynamic fuzzing bridges the gap between static theory and runtime reality, proving definitively how the code behaves under extreme adversarial stress. Traditional automated tools still miss over 80% of complex, exploitable logic vulnerabilities. This bar chart shows the stark performance gap of standard static analysis tools against real-world smart contract datasets. Slither achieves 67.8% accuracy, and Mithril identifies only 72%. As DeFi protocols grow more architecturally complex, relying on syntactic pattern matching to understand semantic intent becomes a critical liability. This scatterplot illustrates the accuracy-efficiency trade-off for standalone large language models. General models fail to optimize both metrics. On the x-axis, models like DeepSeek v3 exceed 14 predictions per analysis. This high average causes severe alert fatigue, wasting manual auditing time. Agentic LLM workflows, specifically frameworks like Smart Audit Flow, represent the frontier of automated auditing. These agentic frameworks do not replace manual review, static analysis, or fuzzing. They act as an orchestration layer for all of them. They utilize multi-objective optimization algorithms, like NSGA2, to track data flow changes and continuously maximize code coverage. NSGA2 is an algorithm designed to optimize conflicting parameters, allowing the system to expand statement coverage while simultaneously maintaining detection accuracy. In a plan-execute workflow, raw static analysis outputs and AST graphs are fed directly into an LLM reasoning engine rather than a human auditor. The core function of the LLM is systematically cross-referencing flagged structural vulnerabilities against the contract's actual semantic business logic. Returning to our initial chart, the empirical results of this synthesized workflow are clear. The Smart Audit Flow framework achieves 100% detection accuracy on standard vulnerability benchmarks. This powerful agentic workflow drastically reduces false positives while catching the context-dependent logic bugs that traditional models miss. In a permissionless, immutable ecosystem, orchestrating the audit stack through agentic workflows provides the high-fidelity verification required to identify logic flaws before reaching the mainnet.